Hello guys, welcome to class today. So let's go through the challenge for this week, which is new architecture, which is CNN. It's a very foundational architecture, so you have to know about CNN, and I'm sure that many of you already know about CNN. And a new data set, which is Fashion Amnist. Of course, it's another historic data set, right? So in the Olympus, like if we had to do a mountain with where we carve all the most famous data set would be Amnist, Fashion Amnist, and CIFAR. So we're going to get to CIFAR next time. And then we're going to discuss activation and pooling. Okay, so because we didn't discuss too much activation in the last challenge, and then the spice for today. The spice must flow. Dune reference will be CAN networks. Okay. So Fashion Amnist, it's the bigger brother of Amnist. Same dataset size, same black and white format, same image format, same number of categories, but we have 60,000 training images. Sorry, we have basically pictures of pieces of clothing, right? So there are shoes, there are skirts, or there are t-shirt, there are pants, there are whatever. Okay, so but what we want to do for now is that we want to introduce CNN. Okay, CNN is a specialized architecture for images, so it would make sense that you start from here. Of course, this is a very small data set, and it's black and white, so also the size of the image is pretty slow. And we're going to move on to CIFAR very soon, and then for CIFAR we're going to have like longer training time, more compelling training data. So makes sense. Okay, good. So remember that this is since it's a standard data set, it's already in TensorFlow or Torch, so you don't have to go download the data set from anywhere. You need to normalize the data set, and you have the different labels. So the first architecture is just to build a simple baseline CNN, right, as we saw last time, and make sure that you set the random seed in NumPy, so that you can reproduce your experiments across different team members, right? So this is not something that we discussed, but usually when you train deep neural networks, there are a few random operations. So the network initialization is random. The split between training and test is random. And so it's important that if you want to share some results, you fix the random seeds so that the results that you see in one run, right, can be reproduced by other team members. So first thing is to investigate the pooling layer. Okay, so we said there are different pooling layers that one can choose. Max pooling is the one that we usually use. So in the baseline, you're going to use max pooling. Then you can experiment with average pooling. Then you can experiment with global average pooling. And then LP pooling. So LP is LP norm, so P equal to 2 pooling. And then you can do some stochastic pooling, right? So introduce some randomness. And then you can train the network over different pooling strategies and see what changes, okay? Because I think you have an intuition of what activation functions do. So activation functions, they describe the type of nonlinearity over which you build your network, right? So rich activation functions, they produce rich behavior of the network, but pooling it's done over multiple channel of a convolutional network. And so I think you have less intuition at the moment on how pooling works and what are the effects of different poolings. So you can experiment with that. And then one thing to notice that if you use the ReLU activation function, then what will happen is that often you will have some neurons are dead neurons, meaning that the connection to these neurons, they are all set to 0. And for how the ReLU works, right, the weights of the incoming connection, they're all negative, for example. The output of the ReLU is always positive. So that what happens is that there are some neurons that they never get active, okay? And so this is because of various reasons, right? So, for example, it's possible that a network doesn't need to have a certain richness in expression, so that some neurons naturally turn off. There is a feature, some phenomenon of feature collapse, right? So, as you train the network, only a certain set of features are relevant. So, if the network has the ability to produce more features, the features are just set to zero. So, there are different dynamics for which we have an intuition that produce dead neurons, but that's something that you can experiment yourself and get a feeling for the dead neurons. In order to avoid the phenomenon of dead neurons, what you can do is that you can change the activation function. So leaky ReLU will have, it's a ReLU where we also have like a small slope for the negative part instead of being fully zero. Soft plus, oh, sorry guys. Double click instead of selection. ELU, tan age, swish. So you can try different type of activation functions. And after you train each model, you can compute the performance, the percentage of dead nodes. So in order to check how many dead nodes you have, you go on your test set and you check whether whether a certain neuron fires during the forward pass for the test set. Okay, and you can see where the dead neurons are. And you can do a very simple table that shows the percentage of the neurons that you have for each different activation function. And then, of course, you can compare the performance for different activation functions, see which one does best. So something else that we have discussed so far is the weight initialization. So we didn't do this for MNIST because however you train MNIST, whatever initialization you try to come up with, MNIST, in my numerical experiments, has only optimal network. Okay, so regardless of the initialization, as you let a training go long, let's say at least 100 iteration, then the network that results, let's say the full dense convolutional neural network, will always collect the same value. Okay, and that's because MNIST is a very simple problem, and so even for moderately large networks, there is only one solution for the classification of MNIST. But this is not the case with fashion MNIST. So as you change initialization, you're going to see that you have different networks that achieve the same performance or very, very similar performance. So what you can do is that you can train the CNN multiple times with different random initialization, and you can record the performance that you achieve and the number of neurons that you have. And then what you can do is that you can try to calculate the distance between the different solutions that you find. Okay, so when you have two networks and you have trained them, then you want to know how close are the weight matrices. You have to remember that there is a permutation invariance. Okay, so if you take two neurons and you swap the two neurons and you accordingly also swap the weights of their connection, then they express the same network. Okay, this is very important. So it's very important to realize that given this symmetry, then you can have different networks that look different, but they have the same weight matrix, right? So in order to check to account for this, what you can do is that you can order the weight matrices, let's say, in terms of raw weight, and then you can verify that the two weight matrices are the same by accounting for permutation. Okay, so make sure that when you compare networks, you account for the network permutation invariance. Okay, and then you can discuss what is the role of the activation function in the role of the initialization on the accuracy, on the amount of dead neurons, and so on and so forth. Then something else that I want you to experiment with is to design your own activation functions and try to see how it goes. And then you can try to come up with your own pooling, right? And here there are some example of different pooling that you can do. And I want you to do this because I want you to realize how hard it is to come up with implementations of these operations that are fast in Python. Okay, so Python is a very high-level language, and so if you do this type of operations in Python, if you don't have some specific module that is able to do this operation fast, then the training time becomes very, very slow. So you can try to experiment a little bit with this, and yeah, just try to come up with some good ideas that you can implement, and then you can implement. And then we come to the last topic, which is CAN, so simplified Kolmogorov-Arnold networks. So CANs were introduced maybe 3, 4, 5 years ago, and basically the activation function is parametric. So you have a certain kernel, and then then you place different kernels on your input space, and then you define the weight of different kernels. And after you do that, you obtain some custom activation function. So it's a way in which you can optimize the activation function of a neuron. With this dataset, the CANs are very slow currently because, of course, they have many more parameters than networks, and the optimization of the kernel, the optimization of the activation function to these different kernels is not as optimized as, let's say, regular backpropagation through a dense layer, right? So they are kind of slow. But what you can do is that you can, since the dataset is slow, you can consider an implementation. And since activation, and you can try to train for this. And you should be able to do this. And then what you can do is that you can plot the activation function that you learn through the CAN network. And then you can try to see if the activation function that you obtain by optimizing the CAN network does make any sense. It provides some intuition of what you should do, right? So as we said, these convolutional filters, right? They often perform some operation which is meaningful for us. For example, a certain edge detection, or detecting certain circles and ovals, right? So there should be some sort of the activation function that you end up having should be something like a thresholding, meaning that you want to know after the feature has been produced if the feature is significantly relevant to indicate the presence of a certain class. Okay. So you can imagine if you have trousers, then you're looking for parallel lines, right? So it makes sense that the activation function will have some sort of thresholding behavior that tells you whether these features are present or not, so that then the presence or the absence of these features can be fed to the dense layers, and the dense layer will, let's say, do a classification of the final class. Okay, and yeah, and the last two sections are all the same. Okay, so that's it. Okay, very good. Let me know if you have any questions. Let me check. Any questions? Otherwise, we do a little bit of convolutional networks, and then I'll let you guys go. Okay. Yeah. Okay. Very good. Yeah, I hope you enjoy this challenge. Again, there is a lot of training in this challenge, but the dataset is fairly small, so the training should be manageable. And as I said, I'll give you an extra week because you're doing midterm week, and I don't. And something that I wanted to stress is that after midterm week, you will be able to choose the members in your group. Okay. So the group formation for this challenge will be the last one, in which there will be the last policy in which we put you in a group where you don't choose who you are with it. And from the next challenge on, right after this challenge, then you will be able to form the groups as you want, and this is an advantage for you. But remember that the price that you pay, for this is that the grade of the challenge will be given uniformly to all the members of the group. Okay. Before we had the intra-team evaluation to share the grade of the challenge based on the contribution of the members, but now you all accept to be in a group together, so your grade will be shared uniformly. And so please be mindful of this, because the psychology that I've seen through the years in which we teach this course is very clear. So the best students, they all want to get the best grade. And so the best students, they tend to coalesce with all the other best students. So there are some groups that are locked in by the smartest, the most, not smartest, the most grade-focused student, let's say, okay? Then there are some people that are just chill and they don't want to push themselves to socialize too much or to reach out to people. And they just settle with the people that have in the same room, in the same group of friends, which is very interesting. And then there is a different psychology altogether, I think, for female students that they like to stay with other female students. I don't know why, don't ask me. I'm not commenting, I just observing. So my suggestion is that you actually consider the group in which you want to be very carefully, right? Because there is a large variance in the group performance, given that the best people go with the best, and then the chillest people, they just choose their roommates. And I think you should try to balance out a little bit your odds, trying to get to work with some students that you like, even if maybe your first instinct is not to be as social as to reach out and try to push yourself, tell people, oh, you should get in the group because I'm the best. I know that some students don't have this type of attitude, which I think it's perfectly fine. Okay, good. No more ramblings. Let's discuss a little bit. Let's remind you a little bit last time what we were doing. So remember that we said, so these convolutional filters, if you go and look for them, what they do, they try to look for shapes, right? They're naturally, the architecture of the convolutional neural network is well tailored to find specific features, and these features get combined by the lower layers of the network. Yeah, so basically, computer vision people, they spend a lot of time trying to design this filter. So if you look at computer vision before deep neural networks, there was a lot of there was a lot of time spent in trying to optimize this type of filters, right? And this type of filters that were then generalized by deep neural networks, so that then once you train a deep neural network, what you actually do is that you reproduce some of the filters that people in computer vision have tried to design for a long time. Yeah, so just some representation of this. Yeah, so this is just to explain to you why convolutional neural networks are good, why we do sliding to capture the same features. So I think this part was not in the original presentation, where it's a little bit repetitive. Okay, so just try to remember the convolution operation mathematically, right? What it does. And the idea is that there is a kernel, right? And the kernel is the one that you are optimizing to backpropagation, and then it's convolved with the image, and then this kernel is shifted around the image, okay? And this is corresponding to the convolution operation as we know it. Okay? So this age equal to k times x. Sorry, convolve. So as we said, most often you will see convolution for continuous function and for one-dimensional function. And so this is some sort of analog to the correlation operation that you also see in statistics when you try to see the correlation between time series or vectors. And this is the cross correlation, okay? So if you have a certain signal A and another signal G, you want to see how correlated is the signal A the signal F at times A and the signal G at time t plus A, so that this final function is a function of the delay between the two functions, okay? So yeah, there is a lot to say about this, but you guys will spend a lot of time on this topic. I think the Fourier transform and the convolution is, you do it in signaling systems and image processing, signal processing. So you should have something like this often. Just remember that also in doing statistics, you will see this type of operation, meaning that when you move to the moment generating function, then you will see that the convolution corresponds to the distribution of the sum of two random variables. Okay, so let's say that we have f of a is a PDF, and g of a is another PDF, and you want the PDF of the sum of two random variables, let's say z equal to x plus y. Then the distribution of the sum will be equal to the convolution of the two distributions. Then usually what you do is that you show that the sum of two random variables will have a moment generating function, which is the product of the moment generating function of x and y. Okay, and basically it will be this same type of derivation, right? So you can move to a certain transform domain, and on this transform domain, the convolution operation becomes a multiplication. So we did a little bit the DFT in the last challenge, so the topic is very relevant, and you're going to see it a lot. Okay, good. So yeah, so just remember the type of operation that you perform, and some of the kernels that you have are a very famous kernel, and you can realize them just by looking at it. So this is the edge detection filter. Usually it's not given normalized, but when you derive it with the CNN, you will have a normalized version. This is the sharpening filters, and yeah, so this is the whole pipeline that we saw so far. Right? So you have the input, then you have a certain convolutional layer that has multiple kernels, and we think of them as being stacked in depth. Then after you do that, then there is an activation function. Then we do pooling. So this is a pooling operation, and then we repeat this a couple of times. So we have different channels, right? In which in each channel you apply a convolutional structure. Then you do an activation. Then you do a pooling. And then eventually you want to get to the deeper layer of the network, in which you switch to a fully connected network in order to take a decision, for example, on which class the image belongs to. And in that case, you just vectorize everything, and then you feed into an MLP, a multi-layer perceptron, and then at the output you have your loss function, so your binary cross entropy, and then you backprop over to everything. Okay. Yeah, so just a lot of representation of this, right? Remember. Yeah, so as we said last time, you can go through this. Just remember that this is the padding, right? So depending, the convolutional filter will slide through the image according to some lag between the different skips, right? And then you have to decide what happens if you are close to an edge, and you can choose the edge values outside of the image boundaries to be either randomly initialized to 0, initialized to 1. Actually, this has a certain influence on the performance of the network, and you have to experiment with this. And this is the stride. We're saying, oh, how does the kernel move? So usually in the convolutional operation, the kernel just slides of one. You can have multiple strides in which you move of multiple lags across two different slides of the network. Something that you can experiment with. Okay, very good. Let's just do quickly the second part of the slides. Remember that we are on this Harvard slide set. Very good. Sorry. Let me share. Go to share. Okay, so we continue from here. Remember that we have this. We discuss some of the images. This is again just a reminder of what happens. So in the full pipeline, we have this, right? So you start with an image which is black and white. Black and white, sorry, a color image. A color image is actually a 3-channel image in which you have RGB, red, green, and blue. And then for each channel, you can apply convolution. So remember, the convolution is applied. Usually, it's applied to one channel at a time. In this case, what we do is that we converted the image into grayscale first. So that we just have the black and white intensity, right? So we just convert the 3-channel into an intensity channel. And then what we do is that we apply a different filter to the grayscale image, right? So this will be an edge detection filter. So the edge detection filter Remember, it's the one with the 8 in the beginning and then all the -1 around. Then you have a blurring filter. This is a sharpening filter. This is the detection of vertical lines. This is the detection of horizontal lines. And then, yeah. So the filters usually are in a neural network. You have different convolutional filters, and then they all are vectorized into a dense network. So, for example, a deep neural network will have multiple 3x3 filters, and you will feed each channel into a filter, and then you will pool the output. So in this case, we have an input which is 32 times 32 and 3 channels. Okay, then you will have a certain filter, and each filter is a 3x3x3, so 3 for the channel, and 3x3 for the kernel size, and the stride will be the 1, and the padding is same. And if you do this, the output is going to be 32 by 32 because you pool over the channel. Then you can ask yourself, how many parameters does the layer have? Because something else to distinguish CNN by DNN is that CNN have much fewer layers than DNN. This is something that you already experimented with in your last challenge, right? When I give you the different number of neurons, and you were constructing different network architecture with different number of neurons, right? So you saw how heavy dense networks are and how much parameters they consume. So here we have, for the first channel, right, we have the number of filters by the filter volume, and then we have to add the number of biases that we have. So the filter volume is here, okay, which is 3 times 3 times 3. And how many filters do we have? We have only one filter, okay? So we have 3 times 3 filter size. So this is, if we go back to the previous slides, these were 3x3 kernels, right? So 3x3 filter kernels. And then we have one for each channel, red, green, and blue. And then the pooling layers, it's same. So the pooling layer doesn't have any parameters. So we have one filter, 3x3x3, and then we have to account for the bias. And the bias is the bias on the activation function, so it's only one. So this whole structure only has 27 plus 1 equal to 28 number of parameters, okay? So in a sense, you can think of it that way, right? So you do the global operation over the image, right? That produces a 32 by 32 output, and this 32 by 32 output is controlled by 28 trainable parameters, okay? So it's a very compact way, compact in the sense that there are very few hyperparameters to describe this sort of global operation that you undergo. So now let's say we have a convolution layer with 16 3x3 filter, and each of them takes a 32 by 32 image as an input. Then how many parameters do we have? So now we just have 16 filters. The volume is 3x3x3, so again 27. And then the number of biases is equal to the number of filters, because each filter has an activation. And so we have 448 parameters, okay? So now everything is remained the same as before, but now we have 16 filters. So yeah. So you see that we have added 16 filters, right? So we multiply by 16 this number. So the output that we have is 16 times this object, but again, the number of parameters is scaled also as 16. So in a dense neural network, this would have scaled as the square, right? Because the matrix will have the scaling is n squared, right? Because the weight matrix is an n by n scaling, but here it's only an n scaling, okay? So that's intuition, right? When you add a filter, you increase the number of parameters linearly. But if you have to double, let's say, the size of the dense network, then you will have that this will be multiplied by 4 because there is a squaring operation in there. So remember that each filter is convolved with the entire 3D input cube, okay? So this is the 3D input cube, but it generates a 2D feature map because what you're doing is that you're pulling across the different channels. And so you just have to remember these dimensions, okay? So in a convolutional layer, we're basically applying multiple filters over the image to extract different feature, but most importantly, we are learning those filters, right? So these filters are not fixed, right? They're not frozen. So when you apply backpropagation, you're learning there. And remember that we are still applying the nonlinearity. And yeah, so this is our friend, the ReLU function. And so after the feature map, if you apply a ReLU, you apply it element-wise, you see here. So the ReLU is applied to all the 2D feature map. And so this is what happens. Yeah, so we want to generate these filters to be rather sparse, right? Because again, they are sort of global operations. So we want this global operation to be, yeah, to be very, to produce a sparse representation of the image, okay? And so the ReLU is something that people really like for that. And then the parameter that we have to define when we design convolutional neural networks is the number of filters, the size of the kernels, the stride, the padding, and the activation function to use. And you should be discovering all of this in the challenge for this week. So when you have in Keras a definition of the convolution in 2D, right, the parameters are this. So the stride is here. So you have a horizontal and a vertical stride. You have the padding. Valid means that you stop at the edge of the image. If you put same, then you put zeros everywhere. Then activation function goes here. If you have a bias, goes here, and the kernel initialization is what you also have in the challenge. So you have this global uniform initialization. Then you have to initialize the bias. If you're going to do a regularization of the kernel, so you can choose to keep the kernel to have unique power just for for regularizing the weights of the network. And then if you have any other regularizer, it goes there, and so on and so forth. Okay. So this is the usual joke. This is the Indian elephant, and you have 5 blind people that touch the Indian. They all think it's a different object because the elephant is so large, but our comprehension of the world is so small. So that's the story. Very good. So then we describe the pooling layer. They activate on each function separately. So here is how the pooling layer goes. So this is the max pooling versus the mean pooling, and that's it. Okay, good. So this should be good. So let's just go to the final example, then we move on. So here you have again the input 32 by 32 over 3 channels. Then we have the filters. There are 8 filters of each of volume 3 by 3 by 3, and then the output will have these 8 channels, right? And each of them it's pooled over the 3. So you will have the 32 by 32. So the depth of 3 is being pooled, and so you just have the 8 layers, and then you can ask how many parameters you have. So you have 8 filters, the volume is 3 by 3 by 3, then the activation function to 8 biases, and you get 224 filter. And as we said, once we get to the end of the filter, then we flatten everything, and then we put everything to a fully conducted network, and then we go to the classification layer, and then we train everything. Okay, good. So these are the different features that we are discussing, and so on. Good. So let's do one more little bit of a quicker presentation, and I'll let you guys go. Because next time I'm gonna move to RNN. So okay, let's do a little bit of this presentation mode. Presentation mode. Okay, so this is the third set of slides that we have for this. So again, we don't need to do a review here. We can move forward. So now we have to discuss the computational network for backpropagation, and we have to understand how to backpropagate through max pooling. Okay, this is what remains for us to understand in order to really know how backpropagation works over CNN. Okay, because basically in the forward pass we have our representation of the various filter, right? So in this case, we have a 2x2 stride 2 filter, right? So this is the activation layer, right? And then we do max pooling, and then we do this, right? So we said 2x2, okay, stride 2. So from here, we're going to jump to the next one. So 8 because it's max. This is 5, this is 6, okay? So we have a mask now that tells you where the position of the max, the max was in each of the different stride, right? So let's go back here, 2x2 layer, and we are doing stride 2. Okay, so we have 2 strides vertically, 2 strides horizontally. In each of them, we find the max and we produce the mask. And then we go forward to our loss function, and then we take the derivative of the loss with respect to the last layer, then the second to the last layer, and our computation network for the backpropagation is coming back to this convolutional layer. So we have these derivatives that arrive, and these are the derivative of the loss with respect to the last layer before the convolution layer. Then we have to remember, right, which weight was picked by the max pooling, because the max pooling has no parameter, right? So we were not optimizing the max pooling. So whatever comes out of the max pooling, we have to backpropagate it through this. So the derivative just is applied to the element that was selected by the max pooling, right? And also here that we set the derivative to 0 with respect to all of the weights, but the ones where the max pooling was selected. Okay, and then this goes back to the weights of the connection of the filter, and then everything goes on. Okay, so these are the derivatives, and then they're applied to the kernel of the filter. Okay, so you see here that basically the elements of the filter were selected were different, right? So this was the bottom left, this was the top right, this was the top left, and this is the top left, right? So they accumulate in the filter this way. Okay. Yeah, so the only thing to remember is that max pooling doesn't have hyperparameters, right? So we just have to sort of backpropagate through max pooling by applying the derivative to the elements that were selected by the max pooling at each different stride of the filter. Good. Okay, now layers have receptive fields and dilated the CNN. So a receptive field is defined as the region in an input space that is particular to CNN feature is looking at. And the receptive field size is crucial, issuing many visual tasks, as the output must respond to large enough areas in the image to capture information about large objects. Okay. So the receptive field is defined as the region in the input space that a particular CNN feature is looking at. So let's see the case in 1D, because the 2D case is just harder to represent. Okay. So here they have the activation map of the element, and this is the 1D kernel, and this is the activation function, and then these are the weights. Okay, omega 1, omega 2, omega 2. Then we move the filter omega 1, omega 2, omega 3, 1. So remember, the elements are the same, and we see which ones is selected by the pooling. Okay, so this is the first one, this is the second one, and this is the third one, and then so on and so forth. And then we have a first layer, right, and that produces this input. And this is the receptive field of 1 by 1 stride, the kernel 3 to 1. And the receptive field for each element of the layer 2 is shown below, right? So you have multiple layers, and they have the input and we are backpropagating and seeing which element is being selected by each of the elements, and we are sort of pulling together these elements into layer 2. Okay, so in 2D it works the same way, right? So we have multiple layers, and you see how each layer extracts information from the previous one, and the receptive field or layer L that we call R0 can be calculated using the recursive formula here, and KL is the kernel size, S is the strides. And for each max polling layer, we multiply the receptive field by the window size, assuming that the size is the same and the window size is the same. No problem. So what we want to know is whether we have a large receptive field or a small receptive field, meaning that if we have a deep network, right, we want to know that a final element in the last layer is able to look at the globality of the image. So we want the receptive field to be large. And if the network is large, then each filter can be small. But if the network is shallow, then we should have a larger filter size, basically. That's what we want to know. So if you go deeper, this resolves the issue, because at each layer we have the chance of pulling together certain areas. But if you cannot go deeper, then you should have a larger filter. Because so if you go deeper, then remember that we have to fight with the phenomena of vanishing gradient versus exploding gradient. And so if you cannot go deeper, you go wider. Okay. And another thing that we can do is that we can inflate the receptive field by inserting holes between kernel elements, and this is called the dilated convolutions. And the dilation rate indicates how much of the kernel is widened. Okay, so before we had here, so now we extend the kernel, but since we want to keep a very sparse kernel, what we can do is that we can decide to skip some of the elements in the filter. So we just insert the zeros there, and we fix those elements to be 0. And here we have the dilation rate of 1, meaning that we skip every other element and the filter only take 1. And you see that the effect of the sliding window is that we still cover large enough receptive field without having too many parameters. And and these are dilated CNF. Okay, so this is a 2 times 2 kernel, and we have stride 1 and dilation rate 1, right? So this is the first filter that takes these 4 elements. Then when we slide, we have this. We slide, we have this. We slide, we have that. So you see that we still allow each filter to collect 2 by 2 elements, but since it's dilated, now they cover a larger surface of the image. A joke, I guess you can say it yourself. Weights and feature map visualization. So the way to visualize what is the way to visualize neural network model? So for logistic regression, we know that we can interrogate the model by printing out the weights of the model, right? And the neural network classifier would be helpful to print out the weights. The answer is no, right? Because it's hard for us to understand how they all contribute together to the output. It's difficult for us to interpret this because the same function may represent 2 very different sets of weight, right? So as we said, dense network are very highly parameterized, so it's possible, and there is the issue of the permutation invariance of the nodes. So you can have 2 networks with 2 very different weights that they represent the same function, and that's because the architecture is overly expressive. Okay, so you can have many nodes that contribute little to the final output, and they are even if they are not dead nodes, so they still activate and fire here and there, then they don't really contribute much because of the cascading of the let's say of the set of small weights. So choosing and designing machine learning visualization requires that we think about why and for whom we need to visualize the weights. So for example, are we trying to diagnose the problem? Are we trying to visualize what the model is learning? Or are we want to teach some concepts? And what you can visualize also changes. We can visualize decision boundaries, or we can visualize the activation pattern, or we can visualize the gradient or the performance of other performance metrics. So to visualize the network weights and activation function as we train, we can diagnose issues with which can ultimately impact performance, right? So what we're doing here is that we have the iteration on the z-axis, right? And on the x-axis, we plot the histogram of the weights. And here we have two different hidden layers. And you see that this layer has very large weights, right? The weights large widely, very widely. So it means that the behavior of the network, it's more irregular in some sense. But here you have a much better regularized network in which the weights are mostly close to zero, right? So the distribution is kind of concentrated around small values. And what we can do is that we can try to visualize the learned filters, right? So what we do here is that we take the image and we apply the filter which is learned by the convolution, which is this here, the learned convolutional filters. And you can see, we can visualize what does each filter do to the image. And since the filters are cascaded, we can also cascade the application of the filters, and we can see what is happening here, right? So you see that some of the filters extract the white areas, some of the features extract the some of the filters extract the boundaries, and so on and so forth. And the occlusion method, oh, that's good. The occlusion method it means that you turn off a certain patch of the entire image, and you see how this affects the classification most, right? So if you take an image and you remove a certain patch, means that all the neurons that were feeding from that patch, they get deactivated, and you can see which patch affects the performance the most, and so that you can have this type of heat map, right, that tells you how much of the accuracy you have lost by patching a certain image, a certain pixel. And so since the patch is sliding away, the patch will correspond to a single pixel will be involved in different patches, and then you can pull together the loss in accuracy corresponding to a single pixel. Okay, and this will give you a heat map of how sensitive is each feature to the classification of the network, right? So this is the example that you do for the label of the horse. So you choose a patch size, and then you plot the accuracy that you obtain by sliding this patch around. Okay, very good. I think we stop here for today, guys. I think we're going to be, I'll let you go back to study for your midterms. And next time, I think we go with RNN, so recursive neural networks, which is going to be very nice for time series prediction. And otherwise, I'm going to be here a few more minutes. And remember that you have an extra week for the challenge. And yeah, I'm going to be here if you want to say something. Okay, guys? I'll stop the recording now. Ciao, guys, on YouTube.